In this video, we're going to talk about section 5.3 in our book, Definite Integrals and Antiderivatives. Remember, as we talk about these rules for definite integrals, what our definition of a definite integral is. It's this limit as n goes to infinity of this Riemann sum, this infinite Riemann sum, f of c sub I times delta x. And we're using, just for the ease of conceptualizing it, our definition that is assuming that the delta x's are uniform in width, but that's not going to impact any of these rules. So in the first one, the integral from a to b of f of x dx is going to be the negative of the integral from b to a of f of x. So switching the order of our limits changes the sign of our result, that integral. And that comes from that whole delta x piece. Remember that our delta x is going to be b minus a over n. And so if we switch the order of the limits, then the delta x will become a minus b over n, and that's going to change the sign. And that's going to then change the sign of the sum. The second one, the integral from a to a of f of x dx, is going to be just 0 all the time. You can think of that a couple of ways. Geometrically, if you have, some curve and you're going to try to find the area underneath a single point, that's going to be 0. You can also see it from our definition of where that delta x comes from, that a minus a over n is going to be 0. And so the delta x that is multiplying f of c is going to be multiplying by 0. The third one, we can pass this constant. So the integral of a constant times a function is going to be the constant times the integral from a to b of that function. And that, again, you can see in our definition that if you had a c out in front, you could factor that out and pass it through, get the sum, and then multiply back by that c. I'm going to slide this up a little bit, hopefully. So our additivity is that if we're, you can kind of imagine here the graph of that. So if this is A and this is B and C is somewhere over here, and we're finding the area under the curve, then you can see that you could add the area underneath the curve from A to B, and then add that to the area under the curve from B to C. So you can split up that interval. So it's going to be equal to the integral from A to C of f of x dx. The second one, we can split those apart, and so it's going to become the integral from a to b of f of x, and then whatever we had, either a plus or a minus, the integral from a to b of g of x. I think that kind of makes sense. The next one is one we haven't really talked about last year, and so let's think about this a little bit. We're going to say that if the max of f and the min of f are the maximum and minimum values of the function on that interval, then, so now what these are really representing is that our max of f is the absolute maximum, and the min of f is the absolute minimum of the function on that interval. So the claim then is that our integral from a to b of f of x, which, remember, I'm going to give you a visual of this here. Maybe I'll say what it is first. It's going to be that the integral will be greater than or equal to the minimum of f, that absolute minimum, times b minus a, and the integral will be less than or equal to the maximum of the function, the absolute maximum of the function on that interval, times b minus a. So the visual that goes with that, if here is our function, say, and we're going from a to b. Let me make this a little more dramatic so we can illustrate a point here. So if we did something like that as our curve, then we can see that the minimum value of the function would be this y value right in here. So there's our absolute minimum, and that our absolute maximum would be somewhere up here, and that y value would be the absolute maximum right in here. So this is the maximum of f, and this is the absolute minimum of f on the interval from a to b. So the claim is that if you look at the area formed by this, the area of this rectangle, which is going to be the minimum, the absolute minimum times b minus a. So this represents the area of that rectangle in blue. Then certainly the area under the curve will have to be greater than or equal to that. And similarly, if you look at the area of the rectangle formed in yellow there, that's going to have as its height the maximum value and as its width the b minus a. And so the area under the green curve will have to be less than or equal to the yellow rectangle, but greater than or equal to the blue rectangle. That's what that claim is making. Okay? Next one I think makes pretty good sense. If f is always bigger than g on the interval, then, then the, hold still, this is my left-handedness not working well with my technology. So then our integral of from a to b of f of x will have to be greater than or equal to the integral from a to b of g of x. I think that makes pretty good sense. And likewise, if f is always smaller than g, then the integral from a to b of f of x will have to be less than or equal to the integral from a to b of g of x. Okay, let's go to the next panel here. So let's do an example here. Suppose we know that the integral from -1 to 1 of f is 5, the integral from 1 to 4 of f is -2, and the integral from -1 to 1 of h is 7. So if we switch the order on those limits, since we know the integral from 1 to 4 is -2, from what we said before, switching the limits is going to change the sign, so that's going to be +2. Part B, if we know that from -1 to 1 is 5 and from 1 to 4 is -2, then using our additive property there, the integral from -1 to 4 of f will be the integral from -1 to 1 of f plus the integral from 1 to 4 of f. And so that's going to be the 5 plus the -2, and so that's going to be 3. And the next one, we can pull the constants out and split those integrals up. So this is going to be 2 times the integral from -1 to 1 of f of x dx plus 3 times the integral from -1 to 1 of h of x dx. And we know from above that the integral from -1 to 1 of f is 5, and that the integral from -1 to 1 of h is 7. And so we just do the arithmetic, and so 10 plus 21, I think, is 31. Okay, next. Okay, now this is an interesting idea, this average value of a function. So we know what an average value of a finite number of numbers is. You just add them all up and divide by the number of numbers. Well, what we're talking about for an average value of a function over a continuous interval gets a little bit abstract here. So what we're talking about, in theory anyway, is adding all of the y values, of which there are an infinite number, from this points on the curve from a to b, and then dividing by the number of numbers that are on this interval from a to b. Well, both of those are infinite quantities, so our average is going to be some kind of infinity over infinity. How in the world do we reconcile that? Well, here's kind of a nice way of thinking of it. Let's imagine first that we're going to take a whole bunch of points, a large number of points that are evenly spaced on that interval from A to B. And we're going to call those, C1, C2, all the way to Cn, where n is a pretty big number. Then we're going to add all of those functional values and then divide by the number of numbers. So using the summation notation, we can write this as the sum I going from 1 to n of f of c sub I over n. Now remember, this n down in the denominator is not variable at this point in time. It's some fixed number. Maybe n is 100, maybe n is 1,000, but it's the i's that are changing. So you're taking f of 1, f of x sub 1, f of x sub 2, f of x sub 3, and so on. Okay, now a little bit of arithmetic here. So we're going to say that our delta x is going to be b minus a over n. So we're taking these points that are evenly spaced. If we divide both sides of that equal sign by b minus a, then what we're going to get is that our delta x over b minus a is equal to, and that's going to become a 1 over n. Now we're going to use this going back to our summation that we kind of left hanging here. Because this n is not varying with the i's, we could bring that n out and write that as the sum I going from 1 to n of f of c sub I. So we're going to replace this 1 over n by this delta x over b minus a. So that is going to make our summation become, now we have delta x over b minus a times that sum I going from 1 to n of f of c sub I. So if we bring this delta x inside the summation but leave the 1 over b minus a on the outside, we're going to get to 1 over b minus a times that sum I going from 1 to n of f of c sub I times delta x. Well, now we have successfully maneuvered this so that what we're looking at here is our classic representation of a Riemann sum, which we know if we take the limit as n goes to infinity. So if we now introduce the idea of letting n go to infinity, then this summation becomes the definite integral. So we still have the 1 over b minus a on the outside, but as we take that limit, the summation becomes the integral. And so this, in fact, is how we find an average value of a function over an interval. We take the integral, the definite integral from a to b of f of x, and divide it by b minus a. So that's known as the average value. Now, if f is integrable on, looking down at the next part, the definition here, so if f is integrable on the closed interval from a to b, then we say its average value is given by what we just set up there. So there's our formal declaration of that. Let's look at the and let's do an example of this. So we're going to find the average value of f of x, which is in this case equal to x squared plus 1 on the interval from 0 to 2. And then we're going to ask the question, does f take on this value for some x in that interval? So first, to actually find the average value, so our average value, I think I'll go to yellow here. So our average value of f is going to be 1 over b minus a, so that's going to be 1 over 2 minus 0, times the integral from a to b, which is 0 to, of our function, x squared plus 1. And so that's going to be 1/2. And if we find an antiderivative of x squared plus 1, we're going to get 1/3 x cubed plus x, and we're going to evaluate that from 0 to 2. So that's going to be 1/2 times the 2. Okay, I'm back. The 2 cubed is going to be 8/3. Oh, hold still there. Going to bring my pen back. Okay, it's going to be 8/3 plus 1. and then we're going to go minus the lower limit, which is going to be 1. And that's, so there's our value. So we plugged in the 2 and we subtracted the 0. So that's going to be, it looks like, I think 8/6 or 4/3 if we believe in reducing. And so there's our average value of that function on that interval. Then the second part of the question is, does f ever equal that on that interval? So for the second part, I'm going to call that part B. So for the second part, the question is x squared plus 1 ever equal to 4/3 for some value of x between 0 and 2? So if we subtract 1, which is 3/3, we'll get x squared equals 1/3. Square rooting both sides, we're going to get the square root of 1/3, which is the square root of 1 over the square root of 3. Now the negative square root of 1/3 is not going to be on our interval, but the positive 1 over square root of 3 is going to be between 0 and 2. So yes, the function does equal its average value somewhere on that interval. Now that's not really surprising because we have a theorem that's coming up next that says that in fact that's always the case. So that's the mean value theorem for integrals. If f is continuous on the closed interval from a to b, then at some point c, the function is equal, the value of the function is equal to its average value. Now there's a visual that's going with this. So there's a picture here that kind of goes with this whole story. So here's our function, say y equals f of x, and it's continuous. We're going to look at this closed interval from a to b. So we know that our average value, this 1 over b minus a times the integral from a to b of f of x dx is equal to what we're calling the average value of f. And so what this really is if you imagine, say, multiplying that b minus a to the other side, so what this average value is telling us, I'm going to just call it, say, k for right now. So this k, if we multiply that b minus a to the other side, we see that this is a rectangle where wherever this average value is, that the rectangle that is k by b minus a, this rectangle is equal to the area under the curve between the curve and the x-axis. That's kind of the visual that goes with that. So that average value is that y value here that will form a rectangle with that little segment from A to B that will have the same area as the area between the curve and the x-axis. Okay, let's look at the next panel. So this is kind of an interesting idea. Our book goes through this, and I'm going to try to go through it with you here. So it's a connection between differential and integral calculus, and this is a real preview or a kind of a justification for the fundamental theorem of calculus. So Newton and Leibniz knew that the quotients of infinitely small quantities, that is dy dx, that is, remember we are taking this limit as h goes to 0 of f of x plus h minus f of x all over h, which can be thought of as a change in y over the change in x as that delta x goes to 0. That's another way of thinking or saying that. So Newton and Leibniz knew that these infinitely small quantities could get velocity functions from position functions. And that's where they kind of came from. They were looking at kind of solving some real life questions. If you knew a position function, how could you get the velocity? They also knew that sums of infinitely thin rectangle areas, This is kind of like what we're talking about with our Riemann sum idea. You're going to add some rectangles and let the width of those rectangles get smaller and smaller. They could be used to get position functions from velocity functions. So they knew of this way to go from position to velocity, and then maybe a different path to go from velocity to position. So some way they have to be connected. And Newton and Leibniz saw that connection, which leads to the fundamental theorem of calculus. So here's kind of an interesting idea. Let's talk about this a little bit. So imagine that we have this whatever function. So I've drawn that function in yellow there. That's our f of x. And suppose we pick any, we're going to start at some number a, and then you can pick any number you like where x is bigger than a. So pick an x that is greater than a. Now, if there were a whole room full of us, we would probably all pick slightly different values of x. And so what we can say then is that this picture represents this integral from a to x of f of x dx. So that is what I have shaded there for my choice of x. And what we would see is that if you picked a different choice for x, as chances are you would, just doing this randomly, then you would have, for you, a little bit different value there. And so what we see is this integral from a to x of f of x dx depends on the x that we choose. That is, it is itself a function of x. And so we can call that maybe, say, capital F of x. So we are defining here this function as an integral. So we have a curve, we picked a point A, and as we choose different values for x, we will find the area under the curve between A and x, and what we get for a number there, what we'll get for our value of capital F of x will depend on our choice of x. Okay? Now, let's see, let's remember then that f prime of x, so we know that capital F prime, the derivative of a function, is the limit as delta x goes to 0. I'm going to say limit as delta x goes to 0 of that change in f over the change in x. So that's our f of x plus h minus f of x all over h coming into play. And then as x gets smaller and smaller, we get a closer and closer to the actual derivative f prime. So let's look at our graph. I'm going to look at the red part here because I don't want to try to erase everything after that. So if we, trying to figure out what color to use here that I haven't already used, kind of used them all up. So our delta f, if we wanted to represent our delta f, the change in f, that would be our change in y. It would be like adding one more little vertical strip right there to that area under the curve. And then that delta f is that area of that vertical segment. The delta x would be the width of that little white vertical strip that I just put in there. And so we could say then that that the delta f, the area of that strip, is going to be then the area of that really, really thin rectangle is going to be, the height will be f of x times the width, which is delta x. Or if we divide that delta x over, we'll see that delta f over delta x is equal to little f of x. And that's what we're trying to get to, because as that delta x gets smaller and smaller, as we imagine that delta x going to 0, then what we're getting here is our capital F prime at x, the derivative. And so that's saying that derivative of that, function defined as an integral is our little f of x. And that's one part of our fundamental theorem of calculus. That's one part of the FTC. Okay, kind of an interesting way of getting at that. Now, let's kind of consider this going a different direction and see if we can get the other part of the fundamental theorem of calculus. I'm going to see if I can slide this up a little bit to get a little bit more room there. So now if we can say if capital F of x is any antiderivative of little f of x, is any antiderivative of little f of x, then we know that capital F prime of x is equal to little f of x. That's what it means to be an antiderivative. If capital F is an antiderivative, then its derivative must equal little f. Well, we know then also, whoops, there's my left hand touching where I don't want it to. Then we also know that if that's true, let me bring my pen back up, then we know that that the integral from a to x of little f of x dx must be capital F of x plus some constant. So there could be some other constant in there. So we can see that if we differentiate both sides here, on the right side we would get capital F prime, which we said is little f of x. And so therefore when you find an antiderivative, you're going to have some other constant c. So let's look at that c a little bit. Let's look at that c and see what we can figure out. So we know from work we did earlier that that the integral from a to a of little f of x, the integral from a to a of anything, is 0. But since we said that the integral from a to x is capital F of x plus c, that means that this x right here also is the same as that x right there. So the integral from a to a of f of x equals 0 means that's also capital F of a plus c. Well, from there we can solve for c and see that that must be a negative capital F of a. So then we come back to, again, we're building on this relationship here. Now we can say the integral from a to b of little f of x dx is going to be, well, let's see, now the b, which again is the same thing that goes here, is going to go there. That's going to be capital F of b, plus we said the c, but the c we said was minus a negative capital F of a. And so this is the second part of the fundamental theorem of calculus. That's the evaluation piece, that the integral from a to b of little f is an antiderivative evaluated at b minus an antiderivative evaluated at a. So kind of an interesting way of looking at it. The takeaway is just that we can use it. So we know that, for example, the integral from 0 to pi of sine of x dx is, we look for an antiderivative of sine, which we know is going to be a negative cosine. And remember, we use this symbolism. We're going to evaluate at the upper limit minus at the lower limit. So we get a negative cosine of pi minus a negative cosine of 0. And since the cosine of pi is -1, the negative of -1 is 1, the minus negative is a plus, and the cosine of 0 is 1, and so we get that that is 2. Very good.